Hi there and welcome to my YouTube channel. In this video we are going to see how we can create mathematically linear regression model without using any sklearn or any library, because this type of question has been asked to me a lot of time in interviews, that can you create a linear regression model with gradient descent without using any other library. Moreover, it is very important to know the math behind linear regression and the gradient descent. By doing the coding by yourself, you will understand the concept and the math behind it. If you have not subscribed to my channel yet, I request you to hit the bell icon and subscribe to my channel now. This keeps me motivated to upload more videos for you. So let's begin. So I have taken a data set of real estate wherein I'm going to take only univariate, that is the distance to nearest metro station, and the pricing of the unit area of the house. Okay, so these are the two variables. So this is my feature, which is the independent feature, and y housing price is my dependent feature, which I'm going to predict. And I can see that the shape of the data is 414, so we are going to split it into train and test. Say 350 we are going to take as train, and rest is we are going to take as a test. And I have just taken some correlation just to check which is the highest correlated, so that we can create a model based on that. So I see that this is having the highest correlation. Based on that, I have decided to take univariate this feature. Then I'm going to just check what is my data type, and then I'm going to scale this particular feature with the standard scaler of sklearn preprocessor. Yeah, here we are going to use sklearn preprocessor, but we can also do this custom made by using mean and standard deviation, but I have not taken that. We are going to only do the mathematical formulation of our model only. So standard scaler is very important, because we will do very much injustice to our own custom model if we do not scale the data, and the results can have consequences. So let's scale it and let's check. Yeah, so we see that values are being scaled, and let's now split the data into train and test. And now I'll just give it a name x and y as my independent and dependent variable respectively, and then I'm going to just go to my four functions. So I have created four functions. The first function is the predict or the hypothesis function. The second is the error. The third function is the gradient, and the fourth function is the gradient descent. You just have to understand this. If somebody asks you in the interview, just think of these four functions and then you start doing the coding. And so understanding deep inside, what's this, what's predict is nothing but y hat, which is mx plus c. It's the equation of the line, but in terms of coding we can say that y hat I, that is for each, y hat I, that is prediction value. How we can get that is with weight 1 multiplied by that xi value, that is the row value of independent feature, plus weight 0. So this is nothing but the intercept. So coming to the error function is the loss function that we are going to use. It is nothing but the summation of y, that is the actual true predictions, minus the y hat. Y hat is the predicted value by our model, and squaring the difference, and then summing all the difference from all the data point, and then taking the mean, dividing it by the number of samples. So this is how we are going to calculate the error. Then coming to gradient, we will have two gradients, one for the w0 and one for w1, that is weight 0 and weight 1. We will always have weight 1 more than the total number of independent features. This is always the concept. So I wanted to explain you in detail how this gradient has been calculated for weights W0 and W1. So for W0 on the left side, if you see, we are going to calculate the gradient G0. Okay, so this is calculated by taking the differentiation of loss function with respect to W0. And if you see on the right hand side, the gradient G1 is calculated for weight 1 by differentiating the loss function with respect to W1. So this is how it is calculated. Now let's go step by step for each calculation. So we have a loss function. It is nothing but the error we just saw, yi minus y hat I whole square summation and divided by n. And now we are going to differentiate it with respect to W0. So here you will see that we are differentiating it with respect to W0. Now on differentiating, we will get 2 over here, that is, it is a square, so we get 2 over here, and we will also get this value as is, because this is how we are applying the multiplication rule. First we will differentiate this value with respect to the order of it, and then we will differentiate the function inside where this W0 is present. And now we are going to differentiate this particular value, because yi will be a constant with respect to W0, and we have this function with a minus sign, so we get this over here as a minus sign, and then we will differentiate it with respect to W0. So according to here in this function also, we see that this is a constant and this will be 0, so we will be left with W0. So W0 differentiation with respect to W0 will be nothing but 1, and here we have minus sign, so minus sign will come here, so it will be minus 2 yi minus y hat I whole summation divided by n will be G0. Okay, so this is how we can achieve G0, that is the gradient with respect to W0. And now similarly we can do the differentiation of the loss function with respect to our W1. Here we see that most of the things are similar, so we will apply this del with yi minus y hat whole square with respect to W1, and then this result will be the similar that we did earlier, that the order of 2 will come here after differentiation with W1, because we are applying the multiplication rule, so it will be yi minus y hat I multiplied by y hat I with respect to W1, whereas earlier it was with respect to W0, here it is with respect to W1. So now we are going to differentiate it with respect to W1 to this function. So W1x will become x. We will be only left with x, and W0 will be constant with respect to W1. So this value will become 0. And so this is how we can get the value xi, and the other value will be similar that we calculated in G0. So this value will be same, only difference will be that there will be one more parameter, that is xi for G1. So we get two gradients, that is G0 and G1 this way. So these are the formula, and we are going to now put them in our code. Now coming back to our code, once we have calculated the G0 and G1, we will now calculate, that is creating a function for gradient descent. So gradient descent is nothing but we are going to update our existing weight with the learning rate multiplied by the gradient. Now we have two gradients, so we will have two such updates for two weights, that is W0 and W1. So this is how we are going to update our weight with each iteration. Whenever one iteration occurs, the weight gets updated, and then we get the error, and now then with the help of the error, that is the loss function, we get our gradient. With gradient we get our weights updated. So this is how this particular stepwise chain is happening each time. Now you might have got some idea how this gradient descent works, and this is the core of machine learning. If you are able to understand this basic thing, most of the things will be clear how this machine learning whole algorithm world works. So let's move forward. So now first I'm going to create my predict function, that is the hypothesis. It's nothing but just the y hat, that is y is equals to mx plus c. Here it will be m will be w1 and x plus w0, which is nothing but the c parameter, which is the intercept. And then I'm going to return this y hat. Then I'm going to create another function, that is, say, naming it error. So inside these I will give these arguments x, y and weight, and I'm going to calculate the length, and then I'm going to calculate my error, and I'm going to update my error starting from something. I have to give a number, then I will calculate for each data point, that is each sample present in my training data, and then I'm going to apply this loss function. This is the loss function that we were talking about, the formula that we created over here. It is nothing but yi minus y hat. This is y hat, and y hat is coming from our predict function. So we are calling our predict function to give us the y hat value by passing each data point value and weight. Okay, and don't worry about this weight, we are going to pass this in our last function, and we are going to square it up, and then I'm going to sum it up, and then I'm going to take the mean of it. So this is how my error, that is the loss, is being calculated. Then moving forward, I'm going to calculate grad, that is the gradient. So I'm going to pass again the same arguments x, y and w. So m, I'm going to calculate the length, and I'm going to give some initial gradient because we need to give a tuple of variant. So it will be an array, actually it will be an array of two numbers, that is gradient 0 and gradient 1. So I'm just applying numpy zeros. Okay, and so I'll be calculating gradient for each data point. So this is the loss function. If you remember, it is minus 2 multiplied by yi minus y predict. Okay, this is for g0, and I'm adding it, and later on I will take the mean, that is I'm dividing it by the total number of samples. Similarly, I'm going to calculate the gradient for g1, that is of w1 weight, and this is how I'm going to calculate it using the same formula that we just saw on the example mathematical derivation. Okay, and then moving forward, I will create another function, that is gradient descent, and in this I will pass these arguments x, y, and then LR is nothing but the learning rate, which is going to be multiplied by the gradient in order to subtract it, that value, with the weight. And epos is nothing but the number of iteration, number of times you want to update a weight to get the optimized weight. Okay, and so we were talking about weights, where we are going to pass it. So we are going to pass this weights in gradient descent function with np zeros, just like we did for the gradient. You saw it here. So it will give us a kind of an arrow with two elements, that is the first will be the gradient the w0, and the second will be w1. And then I'm going to collect a list of errors, collect a list of weights, and I will run it for epos. I've given it 10, and then I'm going to create the error with my error function that I just created. Then gradient I'm going to calculate with the function of gradient that we just created, and then I'm going to update my weight 0, that is my intercept weight. How I'm going to minus the initial weight with learning rate multiplied by the gradient 0. And similarly, I will calculate my weight 1 with learning weight multiplied by gradient 1. Okay, and I'm going to append all the errors on the error list, and I'm going to append all the weights in the weight list. Okay, and this is how I will return my values, the errors, the weight list, and the last weight, that is the latest weight. So this will be our optimized weight. So let's execute and see how our model fits. So I'm executing it. I'm opening this as a unpacking tuple, and let's see the list of our errors. You see that there is a decrease in the error, and let's see the weights. So we get an array of weights of two elements, and let's see what are optimum weights. So we just created our model and we got our optimum weight after 10 epochs, and we have now a predict function with which we are going to now do the prediction on the test data, and we will see how our model is performing based upon various accuracy scores. So let's see. So now we have got our prediction in y hat. So now I'm going to compare my y hat with the actual true values, that is the y test, using various parameters, that is KPIs, to check your model performance. So first is mean squared error, the second is R2 score, and third is the mean absolute error. So let's first check mean squared error. So we got a mean squared error of 0.72, which is kind of decent, and we got R square, which is not so good, but we can optimize it. We will do some hyperparametric tuning and let's see how we can improve it. And we got mean absolute error, which is 0.68. So now let's increase the number of epochs from say 10 to maybe we can do 200, and let's see how our model functions. And the last weight that we will get will be our optimum weight. So I'm not displaying the weights now because it will be too many. So I'm just commenting that out, and I'm going to re-execute my all the functions, and we have our optimum weight, which we will get after it gets executed. It may take some time because the epochs are high, and now we get the optimum weight. So these weight will be fit into our line, that is y is equals to mx plus c. So our y hat, just to explain you guys how this will look like, I am going to just write it so that it's clear. So this will be the intercept. So this will be this will be c, that is the W0, and this is going to be our W1. So this is how our model is going to look like, and this is being multiplied by x. So in our case it will be x test. Okay, so this is our model. This is how our model will do the prediction. We'll get the y hat values, and so on executing y hat, let's see. So our mean squared error has reduced. That's very good news, and this also has increased substantially from 1716 to 55 or 0.55, which is quite a good substantial increase with just number of epochs increase, and we get a good mean absolute error as well. So this is how we can improve with number of epochs, and we can create our own custom made linear regression model. And I'm going to show you with how this looks like, how our error is reducing graphically. So this is how it reduces with each step, each number of epochs. This is how our error will reduce over time, and let's see how our weight looks like over a period of time. So this is how the theta 0 looks like. The weight, it's not changing much, but the theta 1 is changing a lot. So after every epoch, our weight gets updated, that is, it gets optimized. So that's all in linear regression to create your custom model, which can be asked in interview a lot of times, but it is always important to know how you can write your own code, own function. Although there are libraries like sklearn, where you get those packages, linear model, and then you import the linear regressor, but you should know this. So that's all in this video. If you found this video helpful, then please do subscribe to my channel so that you do not miss anything. I'll see you in the next video. Bye.